Hey guys, what's going on? It's Danny, and we're doing another LeetCode review, and we're going to be talking about LeetCode number 198 today, House Robber. We're going to be following the same topics that we've been covering so far in the past few videos, which is just the basic concepts of dynamic programming, which is, I guess to summarize from earlier videos, dynamic programming is the idea of breaking down a problem into smaller sub-problems, and then using those sub-problems, using the solutions to those smaller problems to answer bigger problems, to keep answering the larger and larger problems, which has many different ways, including many different ways to approach, including like memoization. You can use like recursion or building an array, and all these. You can use many different ways to approach it. But what we've been covering so far is array-based solutions, because I find they're the easiest to visualize and the most simple, and what I'd recommend for students just coming out of CSA to kind of wrap their head around dynamic programming. And so to start, we're just going to start by reading the question. You're a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money in each house, return the maximum amount of money you can rob tonight without alerting the police. So, test cases, we have houses. So, okay, yeah. So the array provided to us has houses with values. We have a zero indexed array. We have houses. Let's go with the second example. 2, 7, 7, 9, 3, 1. And now, when I'm looking at this, I'm thinking, how can we scale this problem down, and how can I visualize it? So this is the first way to visualize it, but now, how can I scale it down? Let's scale it down to just 2. If we have 2 houses next to each other, if we have 1 house next to each other, we're going to pick that house. If we have 2 houses next to each other, we're just going to pick whichever one is greater, because we can't pick both, because that would cause the alarm to go off. We're going to pick the greater one, which is the 7 in this case. Now, if we add on another square, if we're expanding the problem slightly to 3, n is now 3, and we have this third value, it becomes more complex than just choosing the greatest value, because if we choose 9, we can also choose 2. And let's say the middle was something like, we're going to make this 10, just for the sake of it. So if we used the previous logic and we just chose the largest value, we'd get 10, and we wouldn't be able to rob the other 2 houses because the alarms would go off. But if we were to rob the 2 outside houses, 2 and 9, we could get a score of 11 money, and no alarm would go off. And now, that right away, this doesn't look like too much of a hint, because I'm seeing, like, how would I know to compare these two compared to these, and how would that scale? So we're going to scale one more. We're going to say we have a third index with a money value of 3. And now it becomes more complex. We can do this one and this one, or this one and this one, or we can skip 2 as well. And now we know the smaller problem. So the smaller answer to this one would be the 2 wider ones, because when we check this one, when we skip back twice, the value is greater. Now, the way we're going to check this thing is we're going to base it on this value. So we're going to make a dynamic programming array which stores all these values. 0, 1, 2, 3, 4. So now at house 0, what is the greatest amount of money you can get is 2. And then 10, and then 11, like we said. So the 2 is calculated with the greatest value, 10 was with the greatest value, and 11 was calculated by skipping the middle. So we took this, at index 2 is 9. 9 is what's stored here. And if we want to add this 9 to the amount of money, in order to add this, we would need to skip the last one. So the last greatest amount we can't use. So we have to go back one more, which is this 2. So if we were to combine this 9 with this 2, whatever is before this 2, all these values can be used. And we can add on this 9 instead of this 10, which frees up this 2. So I think it's a kind of difficult concept, so if we expand it further, I think it'll make more sense. So now that we have this third, in order to include this third value, let's say this was a value we really wanted, this value, if we included it, this second value is done. We can't use this anymore, which means we'd revert back to the one that we skipped, so we'd go here. This 10 plus this 3 is 13, which is greater than the 11 that we would have if we chose not to include this value. So we choose to include this value because if we did include it, the only thing that changes by including this value is this number, including or excluding this. So because we want this more than this, we're going to add it in, and we're going to get our greatest value here of 13. 13. And now we can keep going. We're going to say we have index 4. We'll populate a bit more. And at 4 we have 1, right? Yeah, it's here. In order to find out if we want this 1 or not, let's think. So if we wanted this 1, we would have to get rid of the value before it, which is this 3. If we got rid of the 3, we would add this 1 onto what was the greatest before that, which is 11. So if we added this 11 to this 1, we'd get 12. But this 12 is less than the 13. So why would we include this 1 if what we had before makes the most sense? So we're going to choose to not include the 1 and instead include the 13. Because this element, we're not including it because we want the 3 because that's it's more optimal and it better answers the smaller subproblems that we've been asking. And so I hope you can kind of see how this is starting to formulate. And the next thing we're going to do is we're going to think, how can we store this into an array? So we're going to store this into an array. Expand this a little bit. In order to expand this into an array, we need to think, how many values are we going to have? This is the dynamic programming array, and this is the solution that we're going to be using, which is going to have a length of n. We're going to have 1, 2, 3, 4, 5, 6. And this is n minus 1. So this is the last index of the thing, minus 1. And so now we know the length of our array, which is just n. So we can jump right into the code and declare it. Int myDP equals new int of length nums.length. So now we have the same array, and we're going to be iterating through all the houses and iterating. We're going to iterate through all the houses, and we're going to see at which value is worth including or not, and what the maximum is for each value. So we're going to start at the 0 index. Is this worth including? Does this actually up the value overall in the end? Yes, so we're going to include it. This one does 2. This one does 2, so we're going to include it, but then once we get to this 1 isn't worth adding, so it lowers it, so we're not going to include it. So by looking at this, we can see that if we want to include this 3, we skip 2 back to actually add it. We don't skip 1. So this 3 plus this 1 is greater than this middle index, which is a combination of all of these. So we cross this out, and then we take this value. So now we have a dynamic programming array. We're going to say, yeah, so the first house. So if we're looking at the first house, my DP, or to be consistent with my other videos, the first thing that we're iterating through in this for loop is always my DP. This is good to write down. We're iterating through every value my DP, nothing else. So my dynamic programming array, we want it to equal the greatest possible value. So right now, that's just nums at I, right? And so we had nums at I. Yeah, so this is the base case. This is very simple. And if we were to do this, this wouldn't get us the answer, though, because it doesn't combine. So now, this is for index 0. Let's say we had index 1. How do we calculate this? We're saying my DP at I equals whatever, either, but we have to choose. Do we want to even include this value or not? So the way we decide if we include that value or not is if we lose value. So if my equals my DP at I minus 1, this shows us the value at the index before where we are, which is this 0 index, assuming that we're at I equals 1. And when my DP at I equals I minus 1, we're seeing the greatest value here. So my DP is going to have all the values stored for the locally optimized, which is what this is. At each index, this is the greatest value. So now the local optimization for the I minus 1, if that's greater The only reason we'd want my DP to equal that is if that's greater than the current value, which is nums at I, plus the one that we'd have to take out. So if we include nums at I, we need to skip whatever value is before it, which means that is not included in our best, which means this 3, we want to add to the best of the 2 before it, plus my DP at I minus 2. And now, this is the rule. This is what we're deciding. My DP is whatever is the greatest out of the 2. And one way to write this, you could do for loop or if statements, but instead we're going to actually use math.max, which is takes the largest value out of the 2. We're going to add this as a comma instead. And so now it's going to be the greatest out of the 2. So we look, is the value before locally optimized, is that just better than the value we want to use right now? Or is the current number worth adding on? Is adding that on, losing the last, and going to the second last? So adding this on, losing this, but adding this to it, is this worth it? Is that more? And that's how we calculate each MyDP. But this inherently is going to cause bound errors, which just isn't good, not something we want. So first we need to check is the I in range. So if I minus 2 is greater than or equal to 0, this means that this second statement is potentially worth valuing. So my DP I equals math.max between that and what our current value is. So is it even worth, is my DP worth switching? So if this second bound is in range, is it worth switching to this? And if it is, it'll switch it. But then we're going to check if I minus 1 is greater than or equal to 0. So if the value before it is in range 2, we need to see if that's more worth it. So my DP to I minus 1, if the value before it is greater than what we calculated above, then heck yeah, let's just include what we already have. There's no reason to add to lower the value. Let's just use the greater value that we have from beforehand, which is found here. Let's just use this value instead of adding on this 1 and losing it. Because we added on a 1 here, we'd lose and we'd get like 12 or something, which isn't good. So instead we have this, and now we populate the array. We populate the array. We start with checking each value, and we appropriately populate it as such. And now that we know it's populating correctly, the rule is correct. The exceptions are there, but what are we returning? We're returning, like with most dynamic programming arrays, we're just returning the last index, which is my DP at my DP.length minus 1. So we're in the last index, I'm just going to return that. Now, if we were to run this code, we should get another error because we actually got 3, and that's, I think, it's just because of the math.max, but we don't actually do any adding. The DP array doesn't exactly get initialized. And now here, let's check these test cases. So for this, we actually have put 10. And let's think, what are we missing here? We have a dynamic programming array. We're starting at this first index of it. Math.max between that and that. Wait a second. Maximum money you can rob tonight without alerting the police. And so what this isn't calculating for is it's not adding on this first one. It's only setting my DP equal to 3. So my DP equals math.max. So when I is 2, I minus 2 is greater than or equal to 0, so this code will run. DP at I equals math.max between number at I plus this one, or just that. Here, I'm gonna double check my solution for this one. Oh, it's because the dynamic programming array never initially gets populated. So we need to start out by initializing the array, and that's my DP at 0 equals the nums at 0, because at the very first index of our array, the greatest possible how money we can get is just by robbing that one house. So at 0, it's just worth getting 0. And if we add this in, there you go. So now, the reason why we had that error is because we never initialized our array. The first value of the array, the smallest subproblem, oftentimes it can be best to just initially declare it, which is like what I've been doing in the previous problems, because I find it simplifies things so much. And especially if you're in high school, the focus on complexity just isn't there in a lot of the competitions. So it can be worth it to just have these straightforward approaches. And we pass all these cases. So now if we submit it, we see, okay, we have wrong answer for a length of 2. And the reason we have that is because we don't account for that. We don't account for a length of 2. And if there is a length of 2, let's think, what do we want to return? If nums.length equals 2, let's just return the max of the 2 between nums at I and nums at 1. So if it's very short, we just simply return the greatest one. But then if it starts scaling larger than that, that's when we need to consider these larger extraneous values. Oh, wait. So 3, output is 2. Let that max between... So, make programming array here, 1, 3, 1. So let's just iterate through there. Let's debug in real time. So the first thing of our dynamic program array is 1, and then we're gonna iterate through each value in the list equals. Oh wait. Okay. Yeah. No. We're just gonna straight up debug it. So. If we're starting at index 0 of the just the list, we have this 1, or where's the? Oh, wait. Okay, yeah. So we have this 1, 3, 1. If we're returning this 1 in, 1 I minus 2 is greater than or equal to 0. Nope. So these all return false. So now it's 1 here. Now the second one, I minus 1 is greater than or equal to 0. Math.max between. We should initialize each my dp at I equals nums at I, because then equals nums at I, because at each value that's the base for each value. And I think that by adding this in, this should just entirely switch up the logic. Oh yeah, so there we go. So the reason why it wasn't working originally is because this wasn't accounting for if the current value that we had was just the best one. And that's what it is, because we didn't account, in this one we account for nums at I here, but we didn't account for it here at all. And one way you can incorporate that could also be including nums at I straight up in here. This would change the code, because nums at I could also be a very valid possibility. If nums at I is greater than the other one, you can't max 2 things. So I'm not gonna add that in. But yeah, so to recap our solution, we started by shrinking down the problem. So we looked at the house robbery, we looked at the very first few indexes of it, and we viewed how that affects the other indexes. How does the solution to the first couple affect the others? And that was with the initial declaration of this and the declarations of these. And then we looked back and we compared. We said, if we skip back to, if we're going to skip back 2 values, is including the first value worth it if we skip back 2? Because if we want this one, we can't rob this house. So if we want 3, we want the maximum solution at 1 and beyond and back to be greater than the maximum solution at 2. So it's choosing between the 2 or the 3 to include at each individual point. So we choose between 2 and 3, and then 3 and 1, and so on. And that's what this I minus 1 and I minus 2 is checking. It's checking the index 1 back and the index 2 back to add and see. And then we broke down the problem, connected it like that, and then finally we just returned the very end of my dynamic programming array, because my array is only of length n, and that's the length of the array provided to us. So yeah, so these problems are very common. I hope you can see the connections to the other ones, where This one's not so much Fibonacci. This is a very unique take on, or not a very unique take, but this is just a different, slightly more complex version. I'd say it's more complex than the other two, the unique path and the climbing stairs, because that's basically just Pascal's triangle and Fibonacci sequence. But this type of house order problem, this is a good way to accurately apply dynamic programming. And if you can do this problem, then I think you should feel confident doing a lot of other dynamic programming problems, including Knapsack, and all the other ones on LeetCode. But aside from that, I hope you guys learned something from this video. Maybe understood understood more of the underlying approach to dynamic programming. And yeah, I'll see you soon.